This episode of Real Engineering is brought to you by Brilliant, a problem-solving website that teaches you to think like an engineer. Space elevators are one of those technologies that sci-fi nerds like me obsess over. They straddle the line between outlandish impossibility and genuine engineering potential. It's a technology that could cross the divide of science fiction to science reality if we somehow improved on existing technologies. It's the kind of thought experiment and lofty engineering challenge that could drive the development of future technologies. Necessity is the mother of invention, after all. Before jumping into the technologies that need to emerge to facilitate space elevators, let's first explore what a space elevator actually is. A space elevator is exactly that, a giant elevator shaft that we can climb to reach space, eliminating our dependence on rocket fuel to reach orbit and hopefully, in the process, lower the cost of space travel. This isn't your typical construction that relies on the compressive strength of a material to remain standing. Our buildings are largely restricted in height as a result of the compressive strength of our building materials. The higher we build, the more weight is piled onto the foundations of the building. We can counteract this by widening the base of the construction to spread the weight over a larger area and then taper the building as it rises to reduce the weight being added as we add more floors. The most obvious examples of this are the pyramids, but even the Burj Khalifa uses the same principle, being widest at its base and gradually narrowing to its seemingly impossible height. We can build higher with current materials if we widen the base, but this becomes uneconomic pretty quickly as the base would take up an unreasonable amount of space. So, how would a space elevator solve this problem? By counterbalancing the weight of the structure by pulling upwards. We can do this thanks to centrifugal force. Imagine a tetherball swinging around a pole. At a certain angular velocity, the string will be held straight and taut against the pole, because centrifugal force, an apparent force that appears in a rotating reference frame, pulls outwards. Now, the problem is, the whole point of tetherball is to wrap the string around the pole. If the string can't rotate around the center of spin, it will simply wrap itself around the pole. We are essentially trying to recreate this dynamic, but on an astronomical scale, and to do that, we have to work with the Earth's natural rotation. So, our structure will need to be located on the equator. Let's imagine a base located in the middle of the Atlantic Ocean. From here, we're going to draw a straight line out into space. For now, this is just a line, no structure exists. But any structure that is constructed will need to exist along this line. If it is not in sync with Earth's rotation, the structure will curve and break, or in some sort of cartoon world, wrap around the Earth like the tetherball example. Our orbit will need to be circular rather than elliptical, as an elliptical orbit would require a tether capable of constantly changing length without breaking. We can find an orbit that will achieve this with some simple algebra. To remain in a steady, circular orbit, we need our centrifugal force to equal the gravitational force. Centrifugal force is defined by this equation, where ms is the mass of the satellite, omega is the angular velocity, and r is the distance to the center of the Earth, while the force due to gravity is defined by this equation, where g is the gravitational constant and mp is the mass of the planet. The mass of the satellite cancels out while we manipulate the equations to get a value for r, our orbital radius. Now we have an equation with all the known values, which we can solve for by inputting the values for Earth. And we find a value of 42,168 kilometers. This is the distance from the center of the planet, so we will be about 36,000 kilometers above the surface of the planet at the equator. Okay, this gives us a starting point for our construction. We are going to put some form of massive satellite with a cable into this orbit and begin the construction process. Building up from the planet is not an option, we need to build down. Now this is where things get tricky. If we extend our tether directly down to the Earth, we will shift our center of mass and disrupt our orbit. To counter this, we are going to need to extend our tether in both directions. This keeps our center of mass in geostationary orbit and so maintains our circular orbit. If we place a counterweight on the far end, we don't have to have equal lengths of tether on either side to balance our load, and this counterweight could be a useful platform for operations, so let's do that. Now, something interesting happens when we start to extend our tethers out. Since this is our neutral point where gravitational force and centripetal force equal, any material extending towards Earth will experience more gravitational force, while any material extending away from Earth will experience more centrifugal force. This creates tension in our tether, which will reach its maximum at our neutral point at geostationary orbit, as everything below it is pulling towards the Earth and everything above it is pulling outwards towards space. We can calculate the max tension in the cable with a uniform cross-section with this equation, where g is the gravitational constant, m is the mass of the Earth, rho is the density of our material of choice, r is the Earth's radius, and rg is the radius of geostationary orbit. There is an explanation of how this was derived in this paper, which you can find by matching the reference number appearing on screen now to the reference list in the description. All of these numbers are fixed bar 1, the density of the material we choose. If we choose to build this cable out of steel with a density of 7,900 kilograms per meter cubed, our maximum tensile stress would be 382 gigapascals. That's 240 times the ultimate tensile strength of steel. In other words, steel can't do the job. So, can we solve this problem? Steel is one of the strongest materials we have. We certainly don't have a material 240 times stronger. But we do have less dense materials, which will reduce the tensile stress we have to endure. On top of this, we don't have to have a uniform cross-section tether. Our tensile stress approaches zero at its endpoints, but material at these points have the highest effect on our stress as gravitational force and centrifugal force increases as we move further from our geostationary orbit neutral point. So, it makes sense to minimize materials at the endpoints and maximize it where it's needed most. This will result in an improved design called the tapered tower. So, this brings us to a new question. How can we calculate the area needed at any point along the tether? Our previous paper has an answer once again. This is the equation they derived. Here, AS is the area of the tether we choose at Earth's surface. This starting value will largely depend on design considerations that we can't possibly know right now, but we are going to want to minimize it because this right here is an exponential function, meaning our width is going to increase exponentially as we rise. It is imperative that we minimize this value inside this bracket, and we only have two values we can control in this equation: the density, which we want to minimize, and the stress value, which we are designing for, which here is donated by T, which we want to maximize. Normally, we wouldn't use the maximum stress a material can hold as the design stress. That leaves zero margin for error. We should be designing in a safety factor, but for now, I'm just going to go with it and say this thing isn't going to be safe, and I'm designing it right on the edge of breaking. So yeah, bear that in mind. Remember that strength and density material selection diagram from our last video? Let's refer to that again to pick a couple of materials to analyze the structure with. Steel is cheap and well understood, so let's start there with a high-grade, high-strength alloy like 350 maraging steel. This steel has an ultimate tensile strength that can range from 1.1 gigapascals to 2.4, with a density of 8,200 kilograms per meter cubed. This paper quotes a steel with an ultimate tensile strength of 5 gigapascals and a density of 7,900 kilograms per meter cubed. I don't know what aliens they got their data from, but this is beyond the realm of reality. We will use steel, but with more realistic material properties. Then we will pick some better existing materials. They wisely picked Kevlar, which is a widely available high-strength fiber we could easily form into a tether. We're going to throw two existing materials into the mix too. Titanium, which we discovered in our last video, has excellent specific strength qualities, and carbon fiber composites, which have even better specific strength qualities and would be used today if the SR-71 was redesigned. Using these material properties, we can calculate the taper ratio, which will be the ratio of the area of the tether at the bottom of our elevator to the area of the tether at its widest at geostationary orbit. I'm going to assume a circular area 5 millimeters in diameter at the base. By multiplying the cross-sectional area at the bottom by the taper ratio, we find the cable's widest point. For steel, this taper ratio is so huge that our cable at its widest point will be this number, whatever that is. For reference, the width of the known universe is 8.8 by 10 to the power of 26 meters wide. Even dividing the diameter of this cable by the width of the known universe yields this number, which I still can't comprehend. Titanium is marginally better. Now Kevlar and carbon fiber are looking a lot better. They will have a circular diameter of 80 meters and 170 meters respectively, still not quite feasible. The amount of material required to build something like this would outstrip any cost savings we could possibly supply. And that's just assuming the fibers could even be formed into this shape without losing a significant portion of their maximum tensile strength, which is a big assumption. So I think it's safe to say that right now space elevators are possible in the sense the physics of how they work is based in reality. We just have to make a material capable of making it feasible. Especially when you consider we are analyzing this at the ultimate tensile strength, and in reality we should be using a value below our yield strength, as above that value our material will begin necking, where the cross-sectional area actually decreases as the material elongates. We aren't even considering strain here. One future tech that a lot of people are hyping up for future use in space elevators is carbon nanotubes, whose strength is off the charts, with some studies quoting ultimate tensile stress values as high as 130 gigapascals and a low density of 1,300 kilograms per meter cubed. At that value, the taper ratio is just 1.6. If this material can be manufactured on a massive scale, it would revolutionize life on Earth. But we would still have to solve a huge number of engineering challenges. Eliminating vibrations and waves propagating through the tether is a huge challenge. Powering a climber and dealing with the adverse weather of the lower atmosphere and dodging space debris in orbit are all massive challenges. Before even starting on the most fundamental problem of all, manufacturing carbon nanotubes. We will explore these problems and potential solutions in future videos. One on how carbon nanotubes are made, why they are so strong, and what needs to happen to take them from the laboratory to regular life. And then we will revisit this subject with a design investigation for an actual space elevator using this new theoretical material. During the research of this video, I noticed several mistakes in the paper I referenced. Small mistakes that anyone could make and easily overlook. I only noticed them because I applied their methods myself and noticed inconsistencies. Their rounding was so aggressive that the results were off by an inconceivably large number thanks to that exponential function in their equation, and I noticed that their material properties for steel was incorrect because I recreated their calculations for titanium and noticed it was worse, despite the equation being entirely determined by specific strength. This is the power of applying knowledge yourself, rather than being a passive observer. You begin to understand things on a fundamentally deeper level, and this is why I love Brilliant and believe they are the perfect complement to my channel. I found myself struggling to remember core parts of calculus while following the derivations in the paper, and it's been years since I had to integrate anything. So I have committed myself to completing Brilliant's course on calculus and advanced mathematics to brush up on my math skills, which have dulled with the passage of time. I can complete this course gradually in my spare time, keeping notes and using their mobile app to steal spare time to progress through the interactive courses. This is just one of many courses on Brilliant that will improve my ability to understand the world around me. You can set a goal and improve yourself too, and then work at that goal a little bit every day. If you are naturally curious, want to build your problem-solving skills, or need to develop confidence in your analytical abilities, then get Brilliant Premium to learn something new every day. Brilliant's thought-provoking math, science, and computer science content helps guide you to mastery by taking complex concepts and breaking them up into bite-sized, understandable chunks. You'll start by having fun with interactive explorations, and over time, you'll be amazed at what you can accomplish. As always, thanks for watching, and thank you to all my Patreon supporters. If you'd like to see more from me, the links to my Twitter, Instagram, Discord server, and subreddit are below.